Hello, this is Team SAL's submission to the Fall 2016 Simio Student Competition. Our objective is to create 3 models for a retail company in order to decide if investing in a regional distribution center will increase profits. The 3 models are direct from Asia to local distribution centers, a regional distribution center located in Panama, or a regional distribution center located in Miami. We also evaluated different reorder policies for each model. The reorder strategies are periodic review strategy and continuous review strategy. The outline that we will follow is first, the basic model overview. Second, go over the assumptions. Third, model strategy and logic. Fourth, key performance indicators. Fifth, model verification and validation. 6, scenarios and results. 7th, answers to questions. 8, recommendations. Starting off, we have our assumptions. Results will be based off a simulation run 24 hours a day for 365 days a year. Ships carry a fixed amount for the entire simulation. Ships stop at every local distribution center in a given region. For example, if they are going to Central America, the ship will go to Costa Rica, El Salvador, and then finally stop at Guatemala. While making the model, we decided it would be much more realistic if a ship travels across the Pacific Ocean and stops at all countries in a region. OpQuest does not calculate the optimum value. However, we ran enough replications to assume the results are optimal. There is no warm-up period, so the initial inventory is effective.
This is an overview of our local distribution center model. Ships depart the Asian manufacturing facility en route to Central America, the Caribbean, and South America, where they deliver cases by the thousand.
This video shows our assumptions that each ship en route to a region drops off inventory to all local distribution centers. The ship is traveling to Central America, stopping at Costa Rica, El Salvador, and finally Guatemala. We were only given travel time from Asia to each region. Using crates.com part distance calculator, we were able to determine the travel time between countries. Our model focuses on an alternating state variables, starting out with adding inventory when a ship arrives and subtracting daily demand. To do this, we incorporated source sync timers into our model. The one shown is a daily timer that triggers 19 state assignments, most of which are subtracting, adding, or counting inventory at all distribution centers. In the model, this is depicted using an outdated animation of the sun revolving around the Earth, which is shown in the bottom right. The original reorder point strategy used a periodic fixed order policy. This strategy used a source sync timer for each region, which could be altered in experiments, changing how many days between checking to see if inventory was below the reorder point. If the reorder point was set at a certain amount of cases and the check was set for every week, the entity in the source sync timer will take a week to travel to the sink. Once it gets to the sink, there's a condition saying if inventory of the given local distribution center is less than the reorder point, then an event is fired. This event is a ship being sent to that region. The strategy was implemented for all scenarios, and then all variables are optimized using OpQuest. Continuous strategy was implemented after the periodic strategy was complete. This strategy checks to see when the inventory is below the reorder point using process logic. When inventory drops below reorder point, a ship is sent. The next ship waits a minimum of 7 days, then checks every day after and fires a new ship right when the reorder point is violated.
The next clip is of our Miami distribution center model.
Our recommendations are solely based off maximizing profit. We have included total cost in case this should be considered in the future. The controls in our experiments are the shipment amount to each distribution center, local and regional, reorder point for all distribution centers, periodic review days, and minimum days between shipments. Trace was used to validate all events. We tracked progress of entities through the system to make sure processes were working properly. Models were run for 1 day to ensure all daily cost calculations were correct. Status plots were used to verify output statistics were reporting correct values. The Central America inventory plot shows that daily demand varies.
The profit function calculations are shown above. All calculations were done as output statistics including profit. Below you can see a visual of how profit equals total sales minus total costs. When a ship is sent, a large cost is induced, causing profit to drop significantly. To achieve our results, OpQuest has run a minimum of 2 times for each model. First was with wide constraints to narrow down optimal solutions for maximized profits. When tightened constraints were determined, OpQuest was run for a minimum of 1,000 scenarios with 5 replications. The results from OpQuest were then put into each model and results were verified. Some results were slightly altered after viewing inventory charts to further optimize profits. In periodic, we optimized the shipments for each country, reorder points for each region, and the number of days between periodic reviews. In addition to what was optimized in periodic, the continuous strategy optimized the minimum number of days before reviewing reorder point daily for each region. Maximized profits was the single objective used for all OpQuest experiments.
Here are the inventory charts for our maximum profit scenario. From this we can see maximum profit was achieved by keeping low inventory and having few lost orders.
Here we can see the profit for the local distribution centers using both periodic and continuous reorder point strategies. We can also see how much profit they are losing to lost sales.
Safety stock is additional inventory that is carried to prevent stock outages. It is in place to account for variability. We have chosen not to carry any safety stock in either of the 2 models. This is based on 2 theories. We have used model replications to optimize results. These replications account for variability, therefore we do not need safety stock to account for it. The single objective of our optimization is to maximize profits. Maximum profits were achieved with lost orders, therefore safety stock is not needed.
If cases go to the regional distribution center and then to the country, here are the costs for the different scenarios. The optimum inventory is also shown. The Miami distribution center carries a lot more inventory than Panama. This is based on our optimization that Panama DC will not hold inventory for long. As soon as a ship delivers to Panama, ships depart to local DCs. This method is found to give us the most profit. The sales from the lost profit are also displayed in the table.
We recommend that the retail company should fulfill orders direct from Asia manufacturing facility and not invest in a regional distribution center. The reorder point strategy using local distribution centers that will earn the company the greatest profits in 1 year is periodic. If a regional distribution center were to be implemented, it should be placed in Miami and use a continuous reorder point strategy for greatest profits. Thank you for taking the time to watch the Team SAL submission for the October 2016 Simio student competition.